Let us just understand functional testing. Suppose you have bought a microprocessor from the market, okay, and you are planning to build a bigger system using this microprocessor. Okay, you have designed a bigger maybe a PCB where you are going to put this microprocessor, and you are going to have maybe other components, memory, etc., and you are planning to build a system. Okay. But before you start using this microprocessor, in fact you are not going to build one. You are running a company where you have to build maybe thousands of these. Okay. So, you have not purchased one microprocessor, but you may have purchased thousands of them. Now, you have two options. You can blindly believe that the microprocessor that you have purchased, all the ones which you have purchased are, they do not have any manufacturing defects, right. And then you can plug them into the PCB, you can solder everything, and then turn on some on button and see whether everything is working fine, right. So, that is a bit risky, okay, because if everything works fine, great, then nothing to worry about. But after you plug everything and you turn on the switch, suppose it does not do whatever it is supposed to do. Some things, some lights have to blink, some and when it recognizes there may be a keyboard that you have provided here, and when you push those keys, something is to happen, right. Now, let us say those things are not happening, okay. Then what do you do? What do you suspect? Do you suspect that the microprocessor is bad, the memory is bad? Okay. So, this method where we plug everything into the PCB, assuming that all of these are good components, right, is risky, right. So, a better approach is to first test each of these components. Okay. So, we can test the microprocessor separately, we can test the memory separately, right. So, to test the microprocessor, maybe you have a microprocessor kit. Okay. You may want to insert your microprocessor one by one and then individually test the microprocessor. Okay. And the same thing may be required for the memory and all the other components that are there on the PCB, right. So, that is called as user acceptability test or acceptance test, meaning you are a user, you have purchased a microprocessor, you may have purchased maybe thousands of them, right. Before accepting the package, right, before accepting the shipment, you may want to go and test these guys and see whether there are any bugs. Okay. And if you find out of 1000 pieces, if you find that some 10 of them are not doing they are failing, then you can return them to the manufacturer saying these 10 of them do not seem to work. Okay. So, that is why am I saying why am I talking about user acceptance test? Because as a user you do not know what is inside the microprocessor, right. You know only its functionality. Okay. So, it is as far as you are concerned, microprocessor is a black box. It has many input pins and output pins, okay, and you know its behavior. It has been explained in a data sheet. So, there is a data sheet that explains to you how this microprocessor will behave. For example, if you push the reset button, right, the program counter is supposed to go to 0 and the address bus will become all zeros. So, that is given in the data sheet. Similarly, it tells you how the instructions are fetched from the memory and then how the how many clock cycles are required to execute individual instructions, all that is explained. Okay. It may be implementing some pipeline for the instruction pipeline. There may be all kinds of architectural things which are happening inside. You are not aware of all that, right? You are only aware of the functionality. Okay. You have written some programs and you want them to run, you want them to be producing the right results. Okay. So, you cannot ask the the person who sold you the microprocessor to say, hey, give me the gate level diagram of this, so that I can go and test it. See, you will not get it, right? You have not paid for all that. So, whatever we have discussed so far, okay, all that comes under white box testing. So, we have been assuming that we have the gate level information. We are assuming so far that the gate level netlist is available to us. Okay. So, for example, I know that the gate inside the circuit, this is what it is. So, this information is available to me. If I know this is what is a netlist. Okay. So, there is a simple way we can describe this in a text. We can say input A, input B, input C. Okay. Then we can say D is an AND of A comma B. Then E is NAND of B comma C, and then F is NAND of D comma E. Okay. So, if I am willing to give you a file, okay, this file is sometimes called as a netlist. There may be more than one format. Okay. We have to also possibly write that output F. Okay. In fact, this language that I have just described is used in what are called as ISCUS benchmarks. Okay. So, ISCUS is a conference, and many years ago people who attended this conference, they created a lot of benchmark circuits and they made them available to everybody who was doing research in testing, and these are available. You can find them if you search in the internet, right. So, larger circuits are available. Some of them have hundreds of gates, right. Some of them may even have thousands of gates, right. So, small to large gates are gate level netlists are available, right. So, if somebody gives you the netlist and says, find tests, that is what we have been discussing, the D algorithm, PODEM, right. But here the microprocessor that you have, you only know its I/O behavior. You know, if I apply these inputs, these will be the outputs I can see. Okay. If that is all you know, then you have no choice but to use functional testing. Okay. So, user acceptance test is usually the functional testing only, because we do not know anything else. Okay. And see, it is possibly it builds your confidence when the microprocessor can execute some of the instructions that you use in your program. Suppose you have written a program for sorting numbers and the microprocessor correctly did that, okay, your confidence goes up. Maybe it has that program has used a number of instructions like compare instruction has been used, move instruction has been used, branch instructions have been used, right. So, when you look at that program and it is working correctly, right, at least you know that a number of things are going right, okay. There is no problem in incrementing the program counter, for example, right, there is no bug there. There is no problem in fetching instructions, decoding them, etc. So, you get a little bit of confidence. Then you may take some other benchmark which does let us say some arithmetic instructions, okay. Maybe you have a program for computing the maybe the average of some numbers or something like that, and if that also works correctly, your confidence further improves, okay. But you can never be fully confident that you have tested it and there are no manufacturing defects through functional testing, because there is no end to the number of functional tests I can write. There may be a bug which has escaped, there may be a manufacturing defect that has escaped your tests, right. So, that is still possible, but it is a very common thing to do. People go and do functional testing, and that is only for user acceptance tests. See, the manufacturer, so you must understand that manufacturing test or production test, this production test has to happen on millions of them. The user acceptance test it will happen on a much smaller number of them, okay, maybe hundreds, thousands, because the person who is manufacturing the IC, they will make it in millions, and they may be supplying to a number of different number of different customers. So, you must understand that they have to find fast ways to test these chips, okay. They cannot afford to do functional testing. They must find quick tests which may take, as I explained to you in an earlier class. See, the cost of testing will be prohibitive if they use something like functional testing. It will take too long, right, and the setup will also require a lot of work. So, you cannot practice functional test in production testing. There they will go for white box testing, they will use test generation algorithms and they will have these patterns. So, ATPG patterns are used. Whereas, here they use functional tests. Okay. I hope this point is clear to everybody, why functional testing cannot be used in production testing. Companies may still use a few functional tests, okay. After applying all the white box tests, right, just to get an additional level of confidence, they may run a few functional tests, okay. The ATPG patterns, they do not care about the functionality, okay. So, this particular circuit that is shown here, it may have some functionality to perform, okay. It may have some description, but the ATPG does not care about the description. It only cares about how I can activate a stuck at fault, how I can propagate that fault to the primary output, that is all it cares. Okay. So, that is an important thing that you must understand, right. So, the ATPG test patterns, they do not understand the circuit. Whereas functional tests, they must fully understand it, they must fully understand the test. So, functional tests will be written by somebody who sort of understands the design very well, whereas the ATPG patterns, somebody who, they do not need to understand the functionality. They only need to know how the gates are connected and things like that. Okay. And most ATPG today works only on gate level circuits, right. They do not work on let us say bigger modules like registers, adders, multipliers, etc. Okay. There has been some research on these topics, right, but in practice people continue to use gate level netlists when they are generating tests. Okay. All right. So, let us go back to sequential testing. So, what I was explaining yesterday was you have a combinational logic, you have primary inputs, you have primary outputs, and then you have a register which stores the state, and you have the previous state and the next state. If you are interested in looking at the combinational part, pretending that these are primary inputs and pretending that these are primary outputs, you can sort of write something like this. You can say combinational logic, primary inputs, primary outputs, next state, previous state. Okay. You may assume that initially I am able to reset the flip flops. So, initially you may be able to go to, let us say, all 0 state or something like that. Our intention is I have a stuck at fault here and I want to activate that fault and propagate the fault to one of the primary outputs. Okay. So, unfortunately, you see when I look at this combinational logic, in order to activate this fault, it may require in order to activate and propagate the fault to one of the outputs, it may require a particular state. It may ask you to go to this particular state. I cannot reset the machine to a state, arbitrary state like that. Okay. I can set it to the all 0 state if I want. Okay. So, usually flip flops have a set and a reset. Okay. And usually all the sets are connected together and all the resets are connected together. I can preset all the flip flops to, let us say, all logic 1 state or all of them to the 0 state, but you really cannot assume that you can set and reset individually to whatever you want. Okay. You cannot say I want to set these two to 1, but I want to set this to 0. Okay. So, as a result, you may want to go back and say, hey, if okay, I am going to assume that I can put 1011 here, right. You can assume that I can put 1011 here, and then you can work backwards and say, how do I put 1011 here? Okay. Unfortunately, what may happen is when you go back, it may expect you to, in order to get this 1011 here, I may want to send the flip flop to some other state 0110 state. Then in order to get that 1010 state, it may set you back and say you have to send it to 0010 state, and finally you may end up in a situation where all of them are 0. Okay. So, you can start with the reset state, then maybe go to 0010 and then 0110 and finally 1011. So, this is what you really wanted. Okay. So, this is what you will start with. Okay. You will reset the machine, apply some primary inputs, that will take the machine to 0010 state, apply some other input, it will go to 0110 state, apply some other input, it will go to 1011 state, right. So, finally, you have come to a stage where you have activated the fault, and you will propagate the fault to a primary output. If you are lucky, it will go to one of these POs, okay. But unfortunately, it may go and it may go to one of these, okay. It may not go to the primary output. See, here we have assumed that this is also a primary output. So, the propagation of the delay, the propagation of the fault may happen to one of these guys. So, unfortunately, we have to again continue, we have to again say, this is the next state that we got, maybe it is 0111, right, and this time I apply another primary output, trying to see if I can propagate that fault to another. So, many more cycles may be required. Finally, the output of that finally the fault will propagate to one of the primary outputs. Okay. So, here is when we got the D or D bar, but the D or D bar propagated to one of these states. In the next state, the D may go to another state, and then finally it went to one of the primary outputs. So, D or D bar propagated to a primary output. So, this is too long, takes too long, okay, and very difficult to practice. Okay. So, sequential testing, as you may have noticed, if you practice it as it is very difficult.